Let's start class. Last time we have a introduction to the categorical data analysis. We talk about what is the case, what is the variables, and different types of variables, and explanatory variables. And we talk about response variables, the binomial and the Bernoulli distributions. Okay. So we also talk about the statistical properties for the binomial distributions. Okay, I think we stop here. Okay, so here there's a question. I think I forgot to mention last time. So for the statistical properties of the binomial distributions, we talk about the mean of the y. Y is the number of success for a binomial distribution with the number of trials is n, and the probability of having a successful outcome within each trial is pi, okay, is equals to n times pi. So that's the expected number of success. And the variance is this one. So this is the population, okay, expected value, and this is the variance for the population distribution. And the standard deviation is this one, okay? The reason I said this is the population-based is because, so this reflects the, it's based on the, not based on the samples, but based on the population distributions, okay? And this is the sample estimate of the proportion of the probability of being success. That's the number of success divided by the number of trials, okay? Although the expected value should be the pi, okay? And the variance for the p is equals to this one, okay? And the standard deviation of p is the statistic, right? And the pi is the parameter. I mentioned that last time, okay? If you didn't watch the recording for the first lecture, just review that after class. So the question is, some of you may think about why we need to have a standard deviation of p, which is known, right? Last time I mentioned that this is a statistic which is known, but remember this is random also. Although it's known, but it's random. The random because this p is based on a random sample. If I change a different sample, the p will be different. Okay, so the standard deviation of p is measuring the between sample variation. That means we change to a different sample, the p will be different. Okay, so measuring the variation between the samples. So that's the, and this is also called the standard error of p. Okay. Okay, now let's talk about the likelihood function and MLE, maximum likelihood estimate. These are the two very important concepts in statistics. Okay, so let's consider the data, let's say from a normal distribution. Okay, so we can write the PDF. PDF means the probability density function, okay, which quantify the density functions of a particular continuous distribution. Okay, and we know that the PDF for a normal distribution has a kernel which is this one, okay? So here, this means proportional to that. Why? Because it's not exact. If we want to write an exact one, so there is a constant there, multiplied by this term, okay? So a constant, it doesn't matter. When you do the ratios, the constant will cancel out. So that's why I'm saying I'm just using this, okay? If you want to know the exact formula, you can easily find it, okay? So this one is proportional to this, and we can view the PDF, or we can view this one in two different ways. And these are very critical. Even though you have taken maybe 7,515, I'm not sure if you still clear. So let me just explain that a little bit. So the first view is we can view this one as a PDF function, as I said. So this is a function of x, okay, for the fixed parameter mu and sigma square. For a normal distribution, we have two parameters, right? For a normal distribution, we can usually write a normal distribution with the mean is the mu and the variance is the sigma square. So these are the two parameters we need to characterize a normal distribution, okay? So a PDF is a function of x given the fixed mu and the sigma square, okay? But we can also view it in a different way, okay? So here, another way is called the likelihood function. So what is a likelihood function? The likelihood function view this part in a different way is now it's not a function of x. It's a function of mu and the sigma square for a given x. You see that? Because we have three variables in this function, is that right? X, mu, and the sigma square. Okay, so for the PDF, it's a function of that. But for the likelihood function, it's a function of this. So what does that mean? That means in the PDF, mu and the sigma square is fixed. But we want to have, so x is changed, is a variable. Okay, but here x is fixed. Mu and the sigma square is random variables. Okay, so the idea is very different. Okay, so the idea is the PDF is used to calculate the probability of observing x within a certain range, given the fixed value of the parameters. Okay, so that's why the PDF is related to the probability. We can use PDF to find out the probability. Okay, how to use the PDF to find out the probability? You just do the integrations. Let's say you have this PDF curve for a normal. Okay, so if we want to find out what is the probability for the x is within this range, then you just do the integrations for using this PDF for the x is within, let's say, a and b. And that integrated value is the probability of having x between a and b. Okay, so it's a probability. But likelihood function is not a probability. So that's why you can see the likelihood value can be greater than 1. Sometimes it's even higher than 1,000. It's possible because likelihood function is not a probability. So why we need to have that? Because sometimes we observe the data. So we observed x, but we want to estimate the parameters mu and sigma square. Okay, so that's why the likelihood function is a way that we used to estimate the model parameters. So that's why it's not a probability. okay? But it's useful. Why? Because we can use that to estimate what is the most likely value for the parameter given what we observed from the data. Okay, so that's the difference. So make sure you understand it. So these are the very basic and fundamental concepts in statistics. But sometimes I know people tend to just ignore that, but this can really help you to understand the statistics and the probabilities. Okay, now can we plot the following two likelihood functions? So first, we have a binomial process with 10 trials, but what we observed is 0 success. And the next one is 10 trials, but what we observed is 6 success. So I want to find out what is the likelihood function looks like for these two situations. Okay, so here I posted in the lab notes that, so we have this plot. So this is the sample code. Okay, so here, let's just say, as I said, so likelihood function is a function of what? Is a function of pi, right? And given what we observed, okay? So here, the binom, that shows the density function for the binomial, okay? So this gives the probability, okay? So here we have size is 10. That means we have 10 trials. The probability is P. I set it as a P because here the pi is changed, is a random variable, right? So here the pi ranges from what? So what is the range for the pi? Of course, it's from 0 and 1, right? So in the R, I set the P from 0 to 100 divided by 100. So what does that mean? So that means if, let's say, P equals to 0 to 100 divided by 100. Then you can see what is P. It's from 0 to 1. And the step size is 0.01. Okay, so this, I have the sequence of P. Okay, so after that, so then I write a function. So L1, that shows the density function, or we can say the likelihood function based on the binomial distribution with the P is changing from 0 to 1, with the size is n. Okay, so the next one is the likelihood function given the P is pi is from 0 to 1 with the size is 10. Okay, so here the first one 0 is what we observed is 0 success, and here the 6 is what we observed is 6 success out of 10. Okay, but the probability is changed from 0 to 1. Okay, so you can see now then I plot the P, that's the range for the pi, that's on the horizontal axis. And the vertical axis is the L1, that's the likelihood function for the pi ranged from 0 to 1. So you can see the first one is the red curve. That shows the red curve shows the likelihood function given the 0 success out of 10. So you can see we have the maximum likelihood is at 0. And then it decreases, right? For the 6 out of 10, so the likelihood function is that. You can see the maximum likelihood estimate is at 0.6. Okay, so this is how we plot the likelihood function for the binomial in this case. Okay, so you can take a look after class. And you may ask, so the maximum likelihood estimate MLE is the value of a parameter that maximizes the likelihood function value of what we observed. Okay, so that is a very popular estimate in statistics. And you may ask why we used MLE a lot in the statistics. Okay, that is because MLE has lots of nice properties. The first one is consistency. Okay, I won't talk about the details, technical part. I'm just explaining for the consistency. What does the consistency mean? An estimate is consistent, means that if the sample size increases larger and larger, and you may ask, what is the sample size here? The number of trials. Okay, so here for the binomial, we have two parameters, right? N and P. Okay, so here, if we have more and more samples, so the consistency means that our estimate, MLE estimate, will converge to the true value of the parameter. So that's very nice property, right? And asymptotic normality, what does that mean? That means when the sample size is large enough, the distribution of MLE follows a normal distribution. That's great. And you may ask, why it's normality? MLE is a value. Just as I said, MLE is also random variable because it's based on a random sample. You give me a sample, I can calculate MLE. Is that right? Because MLE depends on the X, and X is random. If you have a different sample, MLE will be different. So MLE is a random variable, has a certain distribution if we change the different samples. And the nice property for the MLE is, when the sample is large, it follows a normal distribution, no matter what the population distribution is. We can prove that MLE always follows a norm. So that's a very nice property. Why? Because for the hypothesis test, for the confidence interval, if we know the MLE follows a normal distribution, we can easily find out some nice hypothesis test statistic. And we can easily construct the confidence interval based on MLE. So that's why we use MLE a lot, okay? Because it's convenient. And the third one is efficiency. Why is efficiency? So the efficiency, that is based on the Kramer-Rao lower bound. If you know that, that's great. If you don't know, so it's fine. It just means among all the unbiased estimate. Okay, so MLE is the one that has the minimum variance. So that's a very good property. Okay, but it's also very tricky. Okay, so it says it's among all the unbiased estimate, it's the best. That means it has the smallest variance. But if you consider also include unbiased estimate, sometimes we can beat MLE a lot. And that there's I just digress a little. So if you know the James Stem estimator, that is biased, but it's performed much better than MLE. So that's a different story. But anyway, this is great. So efficiency. And the last one is invariance. That means if you have an MLE for a parameter, then any function of that parameter, we can still use that MLE. And that will also be the MLE for that transformed parameter. Okay, so based on these nice properties, we statisticians used MLE a lot. Okay, so we need to find the MLE, right? So this just gives you a taste of how to find the MLE. You don't have to find the MLE. So I won't give you any question in the exam to ask you to find the MLE, but this just gives you some taste. So here for the binomial, okay, suppose we observe the data, yi's, okay? Let's say we have 10 observations, y1, y2 to the y10. So we have 10 observations from a binomial with so here so we have 10 Bernoulli trials. I'm sorry. Okay, so that's follow and these are all IID, identical and independent. So this actually is a binomial with 10 and pi. Okay, so here the n is 10. Okay, so here I'm just giving you an example. Okay, so we have 10. So the first, what are the possible values for this y1 through y10? So we have 10 trials, right? Remember, for a Bernoulli, it's just binary. It has either success or failure, right? So here, how about we take the success as 1, right? Because we are measuring how many times of success among these 10 trials, right? So here, each yi can take only 2 possible values, is that right? Either 0 or 1, right? If it's failure, then let's say it's 0. If it's success, then it's 1. Okay? So then we add all the yi's together among these I from 1 through 10. Then it will be what? It will be the number of success among these 10 trials. Is that right? Okay? So yi's are 0, 1. Okay? So we want to find out the MLE. So what is likelihood function? Likelihood function is we observed the y's and we want to find out the pi's, right? So here for each trial, let's say for the first one, if the y1 is 1, okay, let's say if the y1 equals to 1 is success, what is the probability of observing y1 is 1? It's pi, is that right? Okay, if y1 is, I'm sorry, y1 is 0, what is the probability of observing that? It's 1 minus pi, is that right? Okay, so can we write out a formula just to represent that? Yes. So what we can do is we can write pi times y1 or pi to the power of y1 times 1 minus pi to the power of 1 minus y1. So you see, if I can write in this way, it's exactly the same. Let's try it. If y1 is 1, then it's pi to the power of 1, that's pi, times 1 minus pi to the power of what? 0. And that equals to 1, right? So this one becomes pi. And if y1 is 0, then let's say pi to the power of 0 is 1. But 1 minus pi to the power of 1, that's 1 minus pi. You see that? That exactly shows this one. Is that right? So if you understand that, then we can rewrite it to be this one. Pi to the power of yi times 1 minus pi to the power of 1 minus yi. Is that right? And the I from 1 to n. We have n trials. Okay? And then that is what we have. And then we will take a log. And you may ask, why we need to take a log? Because taking the log is convenient, just for convenient purpose. You don't have to. The reason we take a log is to simplify it, because the product after we take a log becomes what? Becomes summation. And the summation is much easier, right? But it doesn't change the MLE. Why? Because the log is what? Log is a monotonic function. If it's a monotonic transformation, then the MLE will not change. Is that right? So that's why taking a log is safe and also convenient. It simplifies. Okay, so we take a log, then it becomes summation. So after we take the log, this can be simplified to this one. Okay, just some mathematics, very simple mathematics. So we have this, and what is this one? These are the partial derivatives. Okay, so we take the derivatives to the pi. Why we need to take a derivative to the pi? Because we want to find the pi that maximizes this, right? If we have a continuous function of pi, how can we find the pi that maximizes this value? Of course, we take the first order derivative, and then we can set these to be 0, right? So that's the common way. So we take the derivative to the pi, and that gives this one. Okay, so from here to here is just simple math. Just log pi, if you take that derivative, that goes to what? 1 over pi, right? And so it's not difficult to check this is this. Okay, so after we get the first order derivatives, then we need to set the derivatives to be 0. Is that right? So these have to be equals to this, because the first order derivative is this minus that. This equals to 0. That means the summation of yi over pi equals to the n minus summation of y over 1 minus pi. Okay, so we have this. Then this can be easily found out. The pi is equals to what? Pi is equals to the average of yi. What is the average of yi? Average of yi means what? Means the sample proportion. Sample proportion. The sample proportion of success, right? So this is the P. Okay, so we can see the MLE is the sample proportion. Okay, but we missed one step. Okay, we have to be rigorous, right? So for setting the derivative to be 0, it has 2 possibilities. One possibility is the maximum. Okay, so that's what we want. Another possibility is not maximum, but minimum. Also can give the derivative equals to 0. So how to check if it's maximum or minimum? We take the second order derivative. If the second order derivative is negative, then it's maximum. If the second order derivative is positive, then it's minimum, right? So we have to do one more step to make sure this is the MLE, not to minimize the likelihood. Okay, so we take the second order, and it is we can easily show this is negative. So then we can prove that the MLE, the maximum likelihood estimate of pi, is equals to the sample proportion. Okay, so that's just give you a taste of how do we estimate the MLE. How do we get the MLE? Okay, and we can use the MLE to estimate the parameter. Okay, so that tells us the sample proportion is probably the best one, is the best estimate to estimate the pi, the population parameter. Okay, so then we can have, so this is what we call in statistics called a point estimate. Okay, point estimate. Why it's called a point estimate? Because it just gives you one value. Is it useful? Yes. But is it very useful? No. Why? Because we don't know the uncertainty. In statistics, so what's the difference between statistics and mathematics? Statistics includes uncertainty. It's not like mathematics, if 1 plus 1 is always 2. Okay, we won't say 1 plus 1 has a 90% of chance to be 2, but 10% of chance to be different from 2. We will not say that in mathematics. But in statistics, we have uncertainty, right? So we need to quantify that uncertainty. So giving that point estimate is not enough. It's good, but not enough. So we need to have some value to quantify the uncertainty about this point estimate. Okay, so that's why we go to the statistical inference. Okay, so the statistical inference includes the hypothesis test and also the confidence interval estimate. Okay, so here I'm just listing, so there are many types of tests. So these are the 3 that I listed here, quite most commonly used. One is the word test, score test, and the likelihood ratio test. So these are the three common tests we usually used to do the hypothesis testing, and particularly for this to estimate the pi in the binomial case. Okay, so for the word test, and by the way, these are three tests are very general tests. It's not particularly for the binomial, but it can be applied. Okay, so here I'm talking about in general situation, and next slide will be the specific to the binomial. Okay, so for the general case, the word test. Okay, so here, before we talk about that, so for the hypothesis testing in statistics, okay, the underlying idea behind the hypothesis testing in statistics is we need to specify two hypotheses. One is the null hypothesis. Okay, so what is the null hypothesis? Null hypothesis is usually something related to no difference, or something that is commonly considered to be correct. Okay, so that's the null hypothesis. And then we need to have an alternative hypothesis, which usually connect to something that has some effect, or something which is different from what we commonly consider to be true. Okay, and then we will find a test statistic. Okay, so the test statistic, and you may ask, how do we find that? Okay, the test statistic has to be performs differently under these two hypotheses. That's very important. If you find a statistic which performs exactly the same under the null hypothesis and alternative, and that test statistic cannot be used. It's not a useful test statistic because it cannot discriminate between these two situations. So we have to propose something. So here I'm talking about very general situations. You may just know the t-test, z-test, chi-square test from 7005 or 15, but I'm talking about more general. Because if you know general situation, you can invent some test using like a randomization test, Monte Carlo test. So these tests, you don't have to use t-test, z-test. You can design your own test statistic. Like a few years ago, I have a client, he's doing some, he has some data set from the PCOM orchard, and he would like to know if the some fungus disease related to the pecan trees is can affect the neighborhood trees or not, or just random. So the distribution of these trees, disease trees are random or have some patterns. We don't have an existing test statistic, but if you know the general idea of what is the hypothesis test in statistics, you can design some test statistic. Okay, so here the test statistic has to be different, performs differently. And then you also need to know what is the behavior of the test statistic under the null hypothesis. Okay, so if you know all this, then you can have a hypothesis test. So you can find the p-values under the null hypothesis. Okay, and then if the p-value is very small, that means what? That means if the null hypothesis is true, it's very unlikely to observe what we had from the data set. Okay, so then that gives us some belief that maybe our assumption for the null hypothesis is true is not right, because it's so unlikely to have what we observe. Then this gives us some evidence that shows the alternative may be true. So that's the underlying idea. Okay, so you can easily see we don't have to have a unique test statistic. So we can have different types of tests, right? So here I'm just listing these 3 different tests: word test, score test, and likelihood ratio test. Okay, so you can see the test statistics are different. The word test is the beta hat is what we observed. So is the test is the statistic based on what we observe from the data set. Okay, so beta hat is the statistic based on the data set that we had. And the beta 0 is the hypothesized value in the null hypothesis. Okay, and the standard error of the beta hat, that shows the standard error for that statistic. And the ratio of this one, it follows a normal distribution under the null hypothesis. Okay, I didn't put the under the null hypothesis, but you should know that. So under the null hypothesis, this statistic follows a standard normal distribution. Or we can take a square, that means it follows a chi-square. Okay, so this is something you also need to know. That's the connection between a standard normal distribution and a chi-square distribution with 1 degree of freedom. Okay, so a chi-square distribution with 1 degree of freedom is equivalent to a standard normal distribution taking the square. So that means so you can generate some random variable from the chi-square with degree of freedom 1 from the z distribution just by taking the square for that random variable. Okay, and that follows a chi-square. Okay, so this is the word test, and the score test is using a different test statistic. The numerator is the score function. Is actually the square of the score function. Okay, so what is a score function? That's the first order derivative for the log likelihood function at beta 0. Okay, and the denominator is the Fisher information. That's the negative expected value for the second order derivative for the log likelihood at beta 0. Okay, so and under the null hypothesis, this test statistic also follows a chi-square with 1 degree of freedom. Okay, and the third one is the likelihood ratio test, which is the -2 times the log of the ratio for the maximum value of the likelihood function under the null and the maximum likelihood value of the likelihood function under the alternative. Okay, and under the null hypothesis, if the null hypothesis is true, this one also follows a chi-square with 1 degree of freedom. So you can see all 3 we're using different test statistic, but they all follows the chi-square with 1 degree of freedom. Okay, and you may ask why we need to have 3 tests, and actually there are more than 3. Okay, so because different tests have some different properties under different situations. Some test performs well in some situation, but not that good in other situations. Okay, so that's why it's actually good to have multiple. Okay, so and we will compare these 3 tests under different situations. Okay, later. Okay, now let's put it to the binomial case. So for the binomial case, let's say the null hypothesis is the pi equals to a certain value, pi 0. And alternative is not equals to. Okay, so the observed data is we have m trials and y success. So the sample proportion is y divided by n. Is that right? Okay, so what is the word test statistic? Okay, so word test statistic follows is just our sample proportion minus the hypothesized value, then under the square, then divide by the square root of p times 1 minus p divided by n. And these are based on the sample proportions. And you can check this is the same as this, okay? So you can see the denominator is based on the sample proportions. beta hat. Okay, beta hat is our sample estimate, which is the sample proportion P. Okay, and it follows a normal distribution, standard normal distribution under the norm. And the score test is this one. Okay, and you can check that. And in the score test, you can see the denominator is actually based on the beta 0, not beta hat. Beta 0 is what? Is the hypothesized value. So that's why you can see in the score test, in the denominator is using the pi 0 instead of P, instead of sample proportion. So you can see this is the difference between the word test and the score test. And both follows the chi-square with 1 degree of freedom. And here, if you take the square, and that also follows a chi-square, okay, with degree of freedom. Okay, so that's the. And for the likelihood ratio test, it's the -2 log for the ratio of the maximized value for the likelihood function under the norm. That's the L0 over the maximum value for the likelihood function under the alternative hypothesis. Okay, so under the no, it's this one, right? Under the alternative, it is this one. Is that right? Why? Because under the no, you can see the first part is what? We all know that. We talked about that last time. That's the binomial coefficient, n choose y. That's the number of ways we choose y from n, different elements, right? And then multiplied by pi 0. Why it's pi 0? Because that's under the no hypothesis. No hypothesis only have one possible value. So that's pi 0 to the power of y times 1 minus pi 0 to the power of n minus y. Okay, so that's the binomial formula. Remember, we have that. This is from here. Okay, this is not something new. Okay. And under the alternative, it's this one. Why? Because the first one is the binomial coefficient. That's the same as this. But what is the MLE under the alternative? That's P. That's the sample proportion to the power of y times 1 minus P over n minus y. Okay, so that's the L1. And then we take the ratio, take the log, multiplied by -2. That will be the likelihood ratio test. Okay, that also follows chi-square with 1 degree of freedom. Okay, so that's the 3 tests in for the binomial parameters. So this slide shows one possible approach that to do the statistical data analysis. But here, this is the statistical analysis to estimate the parameter, to estimate the model parameter, okay? It's not the predictive oriented, so it's not focusing on the predictive analysis, okay? This is basically estimating the model parameters, okay? So we can first consider a very realistic example or problem. Then we can decide on a statistical model. And then after that, we can determine the sample size. Why we need to determine the sample size? Because we want the power of the study not to be low. Okay, so we want to have enough sample size so that we can have a pretty high power of the study. And then we can collect the data. And after that, we can clean the data and then display the data and the statistics graphically and numerically. So these are the descriptive statistics. Then we can do the inference. We can estimate the parameter, like the maximum using the MLE, for example. And then we can carry out the test and compute the confidence intervals or both. Okay, after doing that, then we can reconsider the model. And you may ask why we need to reconsider, because sometimes different models have different assumptions. Is that right? And you will see that in a minute. Okay, I will show you some examples. So if the results doesn't make sense through the diagnostic analysis, okay, then that shows maybe the assumption for the model is not correct. So that may give us to reconsider the models and go back to the estimating using different models. And then based on the result, to repeat that until the model seems to be fine. And then we can, based on the results of inference, and we can draw conclusions. Okay, so this is one possible way to do the statistical data analysis. Okay, so here the major part, so the most important part is actually before you collecting the data, because you need to have a good design of the surveys or the good design of the experiment. Okay, so plan ahead is the key of the success for an experiment or for a survey study. Because if you plan ahead and plan well, the quality of the data will be very good, will be high. And that's the most important thing. Sometimes I see that so many times that people design very poorly. Even though you have a data set or sometimes even large sample data set, but since the design of the study is not good, the results sometimes can be very misleading or just useless because of the poor design of the study. Okay. Now let's see an example. This is the coffee taste example. So here we have a fast food chain considering a change in the blending for the coffee beans. So to determine whether the customer prefers the new blend, so they just have randomly selected 100 customers and ask them to taste the coffees with the new blends and with the old blend. Okay, and so the sample size is 100. It's a binomial process. Why? Because here we have 100 trials, right? And here we assume that uh, the old blend and new blend will have the same chance to be liked by the customers. So here, the null hypothesis will be the pi equals to 0.5. And pi is the probability for the customer likes the new blend. Okay, and the alternative is not equals to 0.5. Okay, and n is 100, right? And we can do the test using the significance level to be set at 0.05. And what we observed is 60 out of 100 customers prefer the new blend. So that's our data. Okay, so we have our P is equal to 0.6, right? So we can conduct the word test, score test, and likelihood ratio test. Okay, so for the word test, this is the formula, and this is the result, so it's 2.04. Okay, and the p-value is 0.041. Okay, so here in the Moodle, I posted in the general information, okay, I posted the statistic tables. You can download it, okay? So here the table, it looks like this one. So this is it has two tables. One is a Z table, the other one is the chi-square tables. Okay, so for the Z tables, if you use the top row, that's for the one-sided. it's the probability for a larger value. Okay, if it's, oh, yeah, it's one-sided. Yeah, so here, let's say we have, what is the 2.04? So what is the p-value? The test is two-sided because the alternative is two-sided, right? So we need to, so the p-value is 2 times the probability of z is greater or equals to 2.04. Is that right? So what is the p-value? So the p-value is you move to 2.04. Okay, so 2.00, you see that in that row? And then you move to the column 0.04. So you go to this one. This is corresponds to 0.04, and this is 2.0. So this is 2.04. And you can see this shows the probability for a standard normal. Okay, this, let's say, is 2.04. Okay, and the area on the right side of 2.04 is equals to 0.0207. And what is the p-value? Then the p-value is 0.0207 multiplied by 2. Because this is a two-sided test, we also need to consider the negative 2.04, which is symmetric around the 0, right? So the p-value is the double the 0.0207. Okay, so that's the p-value. And you can see, so the p-value is 0.041. Okay, and for the score test, the test study is this one, right? Based on the formula, and I do the calculations, it's equals to 4. Okay, so how do we find the p-value? This is using the chi-square with 1 degree of freedom. The test is 4, right? So the p-value is the chi-square is greater than 4. This one equals to 4, okay? So you go to the table. This one goes to the chi-square table. That's the second table, okay? You go to the chi-square. The first column shows the degrees of freedom. Here we are focusing on first degree. So first row, that's the 1 degree of freedom. Okay, so we get 4, exactly 4. So what is the 4? 4 is between these two. Is that right? 4 is between these two values. So goes to the top row, it shows, so the probability for a chi-square with degree of freedom is 1, is between equals to 4. I'm sorry, equals to 4. Is bounded by 0.05 and 0.025. Is bounded by 0.025 and 0.05. Is that clear? So this is the probability of the chi-square with 1 degree of freedom is, is greater equals to 4. Greater or equals to 4, okay? Is bounded by these two. Okay, if I do the plot, the chi-square distribution looks like that. Okay, it's always non-negative. Okay, and let's say 4 is here. Okay, so the area on the right side of the 4 is bounded by 0.05 and 0.025. So this is the reading from the tables. Okay, but of course, if you do the if you use the software, it will give you the exact value. So the software tells you the p-value is 0.046. Okay, and for the likelihood ratio test, under the null hypothesis, the likelihood ratio test is this one. The first one is the binomial coefficient. Is that right? For the binomial coefficient, we have n is 100, right? And what we observed is 60, customer prefers the brand, new brand. So that's the binomial coefficient. Then multiplied by what? Multiplied by this. That's for the under the null. Why? Because under the null hypothesis, pi is 0.5. Okay? To the power of 60, and the 1 minus 0.5, which is also 0.5 to the power of 40, right? That gives this one. And under the alternative, it's this one. And this 0.6, that's the MLE. That's the sample proportion that prefers the new blend to the power of 60, because 60 likes the new blend. And the times 0.4, that's 1 minus the P to the power of 40, that's M minus 100 minus 60, okay? That will be 0.08. Then the likelihood ratio test is the -2 log of the ratio. And that gives 4.04 or 4.03, which is very close to this one. You see that? So the p-value is almost the same. Okay? And you can see when we do the ratios, if you look closely, you can see, does the binomial coefficient matters in the likelihood ratio test? It does not matter, because when we take the ratios, the binomial coefficient, what? Canceled out. Is that right? The binomial ratio canceled out. So if you're smart enough and you do it by hand, you don't need to worry about the binomial coefficient, right? Just cancel it out because it's the same under the null and under the alternative, okay? So what only matters is the rest part, okay, for the likelihood ratio. Okay, let me see. Yeah, for the exams, of course, I expect you can do this kind of test by hand. Okay, and these are very simple. It's not difficult. Okay, so for the other questions, what test should we use? I will let you know. So in the next few slides, you will see I will compare these three tests. Okay, of course, there are many other tests. If you want to include other tests, you can do some research to see what are the characteristics and what are the situations that favors a particular test. Okay. Okay, so now this shows the R code to do the test statistic. Okay, in R. Okay, so here go back to the Zoom, go back to the Moodles in the general informations. I posted in the general informations the link for installing the R and the R Studio. So if you click the link, let's say you go to here, so this will give you the website that introduced how to install the R and R Studio. Okay, and what is R Studio? R Studio is like a very convenient platform for using the R's. So it can help you to edit your code and show and check your grammars in the R's. So it's very convenient. So I strongly recommend you to use R Studio. But to use R Studio, you need to download R first, and then download R Studio. So, and then you need to download some package. So this, okay. So take a look, and you will see the benefit of using the R Studio. Okay, and for introduction to the R, this is a link that shows a very brief introduction using R. Just 5 minutes, you will see what is the R and how to use it, but very brief. For a much more detailed version, you can see this one, okay? And R Markdown is very useful, Okay, so what is R Markdown? This is R Markdown is a file format that combines R code, text, and results in one file, one document. So you can run the R, do the analysis in R, and write the report simultaneously. And it can output several types of format. Some format are like the PDF static, and some format are dynamic, like HTML. Okay, and this is the link for an introduction to the R Markdowns. So for the homework assignment, you can use R Markdowns, and that can be very useful tools for you to for your own research. You can use R Markdown to write the slides, to create the PDF slides, and you can use R Markdown to write your thesis or dissertations, and you can use R Markdown to write a paper. So very convenient. Okay, you can output in Word, you can output in PDF, you can output in HTML. So there are several types of output that you can choose. So basically, you do the analysis and write the report just one shot. So. Take a look if you are new to R's and R Markdowns, R Studios, just check these links and read these documents. Okay, these are the sample code for you to find out the test statistic in R. So I think I can just skip these because it's quite straightforward. I use several functions in the R, like the P norms, like the SQRT, that's the square root, and the P chi-square, that gives you the probability of based on the chi-square distribution with degrees of freedom is 1, and this. If you want to check what does P chi-square means, you can just, as I showed last time, go to the R or R Studio. You can also use R Studio. So just type in the question mark and the function name, just take the returns. It will show you the help menus, and you can see that. Okay, so very convenient to use. Okay, so after that, what is our conclusion? So the conclusion is for the coffee taste study, all three tests give us the p-value is less than 0.05, but they are all very close, right? So do we reject the null hypothesis? Yes, but barely. It's marginally reject the null hypothesis, right? Isn't the alpha equal to 0.05 significance level pretty arbitrary? Yes. But most of papers, most of journals like to use that, okay? But if you insist on a yes or no question using the alpha 0.05 can give you the answer, yes or no, okay? Answers. And what do we conclude from this study? So the results shows a significant difference in preference for the in preference for the two blends of coffee beans. Specifically, more consumer prefers the new blend. Okay, so this is the conclusions. And what if the results are not significant? Should we say we will accept the null hypothesis, or what should we say? So this, we can usually say this study does not provide clear evidence that the consumer prefers one blend of coffee beans over the others. Okay, so the results are consistent with no difference. Or we can say we have, but this doesn't mean that the null hypothesis is true, or this doesn't mean that alternative hypothesis is false. If we if the results are not significant, because they can have different reasons to lead to non-significant results. For example, if we have a small sample size, so the power of the test will be low, right? So when you interpret the result, you have to be careful and accept the null hypothesis or fail to reject the null hypothesis. Usually, we prefer the fail to reject the null hypothesis. Okay, so so have the large p-values that leads to fail to reject the null hypothesis. Okay. Okay, now let's talk about the confidence interval. So in practice, which is more informative, the p-values or a confidence interval? Okay, many people prefers the p-values, but in fact, the confidence interval approach is more informative because we can use the confidence interval to conduct a hypothesis test. And also the confidence interval provides more information than just giving you the test results, hypothesis test results. Okay, so what is a confidence interval? So confidence interval is actually inverting a hypothesis test. Okay, so suppose, let's say the significance level of a test is 0.05. Then we have the confidence level for the confidence interval is 0.95. Okay, so the confidence level is just 1 minus the significance level of a hypothesis test. And then the 95% confidence interval is what? Is the set of the parameters, values, that makes the p-value is greater than 0.05. So you can see there is a direct relationship between a confidence interval and hypothesis test. So that's why we can conduct the hypothesis test through a confidence interval approach. Okay, because the confidence interval is nothing but a set of parameter values that gives the p-value greater than 0.05. In other words, if the confidence interval includes the hypothesized value, then we say we fail to reject the null hypothesis. If the confidence interval does not include the hypothesis value, then we say we reject the null hypothesis. You see that? So we can do a hypothesis test through a confidence interval. Okay, so what is a 95% confidence interval based on a score test? Very simple. Just based on this definition, we know that a 95% confidence interval based on the score test is the set of the pi zeros, the set of the pi zero values, such that the score test statistic is less than 3.84. You may ask, what is the 3.84? What is that? Where does that magic number come from? Because the score test follows what? Chi-square distribution. Is that right? Score test follows a chi-square distribution. Okay, 3.84 is what? Let's go to the table. 1 degree of freedom, 3.84 is this magic number. You see that? That corresponds to 0.05. Okay, so that's the threshold. That's the cutoff point. So that's where the 3.84 come from. Okay, it's actually 3.8415. Okay, so here, so these just gives you, so the 95% confidence interval based on the score test is nothing but the set of the pi zero values such that the score test statistic is no greater than 3.84. That's it. Okay, so and similarly, what is a 95% confidence interval based on the likelihood ratio test? It's the set of the pi zero values such that the likelihood ratio test is less than 3.84. Okay, so let's see an example. Now, for example, let's see what is the confidence interval for a word test. Okay, So based on the definition, we want to have the word test statistic to be what? Less than. Now this time we are not doing the 3.84. For the word test, we can do it in two ways. One is it follows a normal distribution with 0. Or standard normal distributions, right? If we take the square, then it goes to chi-square, okay? But we just do it from here. So to do it from here, what is the region that we fail to reject null hypothesis using the word test? We go to the table. Now this time, let's say we go to the Z table, okay? So to fail to reject the null hypothesis, standard normal, right? So here the alpha is 0.05, right? Remember these are two-sided. So for a two-sided, what is the rejection region? Rejection region should be, one tail should be what? 0.025. That's the right area, right? Left area is another 0.025. If we add them together, it will be 0.05. Is that right? So what is the rejection region? Let's go to the table and then find the value. So here the table shows the probability of larger value. So we go to 0.025. Is that right? 0.025. You see that? That number here, right? 0.025. Okay, if you go to here, it's 1.9, right? 1.90. If you go to the top, 6, 0.06. So that means what? This is what? 1.96, 1.96. Is that right? So then we say, okay, so this is nothing but we want to have this W to be less than 1.96 and also greater than what? Negative 1.96. Is that right? So this is greater than 1.96 and larger than negative 1.96, okay? So here I'm setting the alpha is to be 0.05. So then this will be 1.96 and also it should be greater than negative 1.96. So this is the region 1. So this is the region. So within this negative 1.96 and negative 1. We fail to reject null. Is that right? 1.96. Okay. Okay, so then you may say, okay, this is alpha is 0.05. What if we have more general results? So that's why I'm not using 1.96. That's why I'm just saying this one is what? Alpha with the Z with the subscript is alpha divided by 2. Now you know what does that mean, right? So our Z with the subscript alpha divided by 2 is nothing but the cutoff value, okay, that has the right area is equals to alpha divided by 2. Does that make sense? Okay, now this one, I use the negative Z alpha divided by 2. So that is the threshold, that's the cutoff point that has the left area is equals to alpha divided by 2. Okay, so these are the notations. Okay, if you understand that, then the rest are very simple math. Is that right? And by the way, you may ask why there's an n here, because it should be divided by n. It's just I flip the n to the numerator. Okay, that's nothing. It's not a trick. It's just this is equivalent. Okay, then I just do the divided both sides by the inverse of that, and then do some addition, subtractions, these things, and you can easily find the confidence interval is this one. Okay, it's very simple math. Okay, so the confidence interval has the upper bound is this one, lower bound is this one. Is that clear? So that gives the confidence interval based on the word test. Okay, and you can also do it on the score test and the likelihood ratio test. Okay, but I tell you, likelihood ratio test is not that easy to do. Okay, so the reason I do it on the word test is because this is the simplest one to do it by hand. Some of these are not easy to do it by hand. Okay, so now we can express the confidence interval by P. That's our point estimate, MLE, plus minus this one. Is that right? Because the upper bound is P plus this one. Lower bound is P minus this one. Okay, so it's P plus minus this one. Okay, also we can write it in this way. And this plus minus, this part has a name called the margin of error. Okay, margin of error. So if the alpha is 0.05, then the 95% confidence, 95% margin of error is about this one. Why? Because 2, why is 2? Because this one is what? 1.96. Remember? 1.96, right? Which is very close to 2. So basically, it's double the square root of this. Okay? Okay, so now based on the word test, and we got the 95% confidence interval for the taste, coffee taste example is 0.504 and 0.696. Okay, so how do we report our results? We can report that now the estimated proportion prefer the new coffee beans blend is 0.6 plus minus 0.096. Or we can say the 60% of the consumer prefer the new blend because the 60% is our point estimate. These results are expected to be accurate within 10% points. Why within 10%? Because what is the margin of error? The margin of error is about 10%. Is that right? So we say the results expect to be accurate within about 10%. Okay, so 19 times out of 20. Why is 90 times of 20? Because that's 95% means. 95% is 19 out of 20. Is that right? So that's what it means. Okay, for the interpretations of the confidence intervals, very tricky. Okay, when we show these confidence intervals, and when you interpret, you have to be very, very careful because here, what is random, what is fixed? Okay, when we have this confidence interval, 95%, we said is this confidence interval has 95% of chance to capture the unknown but fixed parameter. That is what it means. Okay, in other words, if I resample the data many, many times, let's say we resample the data 100 times, and out of these 100 times, each time we can construct a confidence interval. Is that right? Based on the data. We have 100 data set because we do that 100 times. And we have 100 data set, we have 100 confidence intervals. And all these 95% confidence intervals, among these 195% confidence intervals, we expect 95 of these confidence intervals will catch the true unknown parameters. That is what it means. In other words, those upper limit and the lower limit that we got from this confidence, these are random, but the parameter is fixed. You see that? That is, okay? And many people interpret in a very different way, says that this confidence interval can catch that random parameter 90% of times. So this seems to be the parameter is random. No, the parameter is always there, is fixed. But what is those limits are random. Okay, so that's why, I don't know if you know the Bayesian statistics. In Bayesian statistics, there's no confidence interval. There's credit interval, because the credit interval is different, because in Bayesian statistics, we are not assuming the parameter is fixed. We are assuming the parameter is random. So in the credit interval, it's actually the 95% of chance this random parameter will fall into that credit interval. So that's why in Bayesian statistics, we have a different name. That's called the credit interval. But in frequentist, we have the name, it's called confidence interval. Very different. Because what is random, what is fixed are totally different. Okay, so these are those basic concepts in statistics. I think it's very important for you, and that can help you to understand what is a statistic and what is statistical inference. Okay, I think it's worth to do it slowly at the beginning for this course, because I need to make sure you understand these basic concepts. Then we can go faster. Okay, so any question before we start? Okay, so let's stop here.